what is this Darlington Emiter follower class? Why is this means sometimes you will just impedance matching. So you need impedance matching, that is high input impedance and low output impedance. That's what Darlington Emiter follower does. The input impedance of this amplifier is very high and the output output impedance is in terms of tens. So that's why we use this amplifier. Whenever we convert high impedance to low impedance, we are going to use this amplifier. Let's design. This is the Darlington Emiter follower. Two ampere transistors are Darlington pair. Okay, let's redesign the circuit. Okay, circuit elements. Okay, first design of basic circuit. Okay, let the given value state is the given values. That's why VC is equal to 6 volts and IQ is the biasing. Okay, bias. Why I am taking this session IQ means here we are taking out the emitter. So that's why our here is not a IC is not our output. IE is our output. Okay, and then on almost these amplifier voltage gain is a unity gain. Okay, and the current gain almost is very high. Also we will see in the derivation in next video. So that's the current gain of one amplifier into current gain of second amplifier. That's the total gain. If you take a current gain, that's the total current gain. That's the AI1 into AI2. That means current gain is a multiplier of two transistors. And then almost these amplifier output is with the follows the input. That's what is called emitter follower. Okay. And then let's redesign this. It's a given values. My VCC is at 12 volts. So how much it has to keep VCC means that's like 2 times of VCE. That's the VCE. So my VCE given value is at 6 volts. So that's a 2 times 12 volts. Okay. Let's make some assumptions for the design. So that's it. For my first assumption is that ID is almost equals to 0. Then second assumption is that VD equals to 0.5. Okay. Let's design a I. So this, what is this resistance? This resistance is this voltage. That means whatever emitter current going through that is this way. Okay, this is the I, right? Yeah. And then that resistance equals to this voltage. Let me V is a V divided by IA, that gives RE. Okay, that V is equals to 6 volts and then my I is a given value. Okay, 10 milli. That gives 0.6 kilo ohm. So we don't have 0.6 kilo ohm standard value. So we will use 560 ohm. Okay, and then the next step is next step is voltage across this. This is my biasing voltage. Let's call this V. This voltage equals to this closed loop voltage. Let's apply it here. That's a VR2 minus VDE1. This is this and emitter resistance. This is 0.7 and then VDE2. That's also 0.7 and VDE that's a 6. So that gives me the 0.7 and VD1 plus VD2 and VRE. That's 0.7, 0.7 and I into RE, that gives RE. VRE, that's a total voltage is there. VRE2 voltage is there, 7.2 volts. Okay, now let's come back to the output section. So this is my output section. This section. Okay, this is the output section. So let's apply a KVL on this code. Okay, that's a VCC equals to, that's a VCE plus VRD. Okay, that's a one of the equation. And apply a KVL at the input section. This is there. Okay, that is this is the biasing section. So that gives me VCC is equal to VR1 plus VR2. That's the equation. Okay, then what's the VR1? That's the VCC minus VR2, right? VR4 already VR2 here. How much is that? 0.1. And my VCC, we know that my VCC is a 12 volts. So that gives me 4.8 volts. Okay, and then IC is a, this IP2 is a IC divided by HFE. This HFE nothing beta. Okay, and then we know that IC almost is equals to I, that is a 10 milliampere. So that's our first assumption. Okay, from that our beta is a 100. So we are defining, no, not defining. So let's define that is a 100. Okay, and then that gives me the 0.1 volts. That means the biasing current for this biasing resistance is a 0.1 millivolts. Okay, then what is this? This is the resistance. Okay, and then we have 2 voltage, and that was the 10 times of IP1. That means this voltage. That gives me the 4.8 into this 10 microfarad again gives me the IC1. This is the IC2 actually. That taken its output. This IP1 is gives IC1 divided by, and then IP1. That's again 0.1 divided by 1. That gives me the almost 10 microamperes. Oh no, 1 microampere into 10. That's a 480 kilowatts. Okay, and then R2. How do you define R2 is there is 10 times of current flowing in this branch is there is only 1% of current flows through this base. We know that base current is very less of a resistor. Okay, and then 9 times of remaining current flows in a R2 resistor. That's this one. So that gives me the 7.2 and divided by 9 into this is the my first ID1. That's a 9 into 1 microampere. That's the 800 kilowatts. We use no standard of 800 kilowatts. We use I20 kilowatts. This is about the I'll explain what is bootstrapping. This is the design of bootstrapping. Guys, till now what I have explained, that's a without bootstrapping. First of all, let me explain what is the bootstrapping. Bootstrapping is defines, that means it justifies that the common collector, that means emitter for our amplifier is a unity gain amplifier. How we will see in this case. So what happens when you feed an input directly to this input, base, this external network will be called bootstrap network. So this capacitor will choose even for very low frequency, this capacitor acts as a short. What happens this capacitor acts as a short means this whatever you the voltage applied, that directly appears with your output. Okay? And then let me explain, without bootstrapping, what happens? Without bootstrapping, we tell circuit. What happens when you do an AC analysis? What you will do? You will ground the DC component. If you ground it's a DC component, means what happens? That's a R1 parallel with the R2, right? You see that? R1 parallel with R2, you are taking an output at the RV, okay? And then R1, R2. Now measure your input impedance, your ZI. What is your ZI? That's a R1 parallel with R2, and we know that's a that's the internal resistance of this network, which is the common character network. That's a HIC. So we know that. Then what happens is ZI. That's ZI is equals to R1 parallel with R2 parallel with HIC. Then we know that the HIC is very high compared to R1 and R2. But what happens when you do the exact analysis? That's parallel resistance almost decreases, right? Decreases. That means your ZI input impedance is decreased. That's why we are not going to use this circuit. That means this is without bootstrapping. Let me see. Let me explain with bootstrapping what happens. Okay, this is a bootstrapping circuit, and when you do an AC analysis for this circuit, what happens? So ground is the DC components, and that gives me R1 parallel with R2 series with the RB. Now take your HIC, this is your Now take it regularization. That's a RB plus R1 parallel R2 parallel HSC. Now let's see, you can see that your Zn is equals to RB plus R1 plus R1. Even though if you decrease your resistance, this is a parallel resistance, that RB may correct. RB will choose such that the resistance of the in terms of few mega ohms. That's it, like that. Okay. This is all about the bootstrapping, and almost with the bootstrapping and emitter follower, the voltage should be unity only. So we will see that that's enough practical. This is all about the theory. Let me see. And how we will measure the same concept what I explained in my previous session videos. The same concept we will use to measure Zi and also in this case amplifier we will only bother about the impedance, not a voltage. I told now it's a voltage gain, it's a unity. So how to measure your Zi? So let me take this is CC arm, okay, and same as series with the, and please make series connection with some fixed resistance. That's make around it's in 1 ohm or 2 mega ohm. That's in mega ohm, and your DRB. Please use this DRB in terms of 1 mega ohm. Okay, and connect it as series. Okay, and observe your output and wherever for what happens at a certain resistance, at a certain point, your output becomes off of that. Right? Off of that. Then remove it. Okay, whatever the procedure previously we done, same procedure. So switch off the power supply and remove it and measure the total resistance with the fixed resistance and DRB. Check the input resistance, that's your Z. Okay, and then what is your Z0? Your Z0 is the same as parallel with the DRB output. And please don't put a mega ohm DRB in this case. Put a 1 kilo ohm, around 1 kilo ohm or a 100 ohm resistance. Why is the output resistance is very low? We are asking defined is in a tens of that. So that means this RB defined is in 470 ohm, right? It should be less than 4. It's not a 470, sorry. It's around, we are designing value is 500 ohm, right? So it should be less than 500 ohm. That means it's in terms of for a Darlington Emiter, it is in terms of hundreds. Okay, with bootstrapping, so that's in terms of tens. Okay, this is all about the how to measure impedance and gains. So let me see the practical case how we will calculate and how we will extract these components from this. Okay. Come back to the practical session of emitter follower. I'll use a 1 mega ohm pot plastic package. Okay. Guys, it's a 12 volts VCC. You can see that it's a RPS 12 volts VCC, and then it's a oscilloscope. Please keep it in some threshold frequency. That means where your gain is constant. So of course you just kept it as a 10 kilohertz. That's enough. Okay. We can see that at 10 kilohertz, the input almost equals to output. That input follows the output, and then that's the input. That's input is a 2.8 volts and the output is also 2.8. So if you take a gain of that, so you will get a unity gain. So that's without DRB. Okay. Guys, now I connected the port and we can see that at a certain level, so that output is the output exactly reduces to half of the input. Now we can measure the resistance by using a multimeter. We can conclude that what is the input resistance by this. Okay. Guys, we can see that almost we are getting 700. That's in a 2 meg. That means almost it's a 700 kilo ohms. That's in a kilo ohm. Okay. This is about the without bootstrapping. Let me connect the bootstrap. Then we will see the. Without bootstrapping output impedance, you can calculate. I connected the 1 kilo ohm, 1 kilo ohm port, and output is exactly reduced to half of that. So now we will see the output of the port. Okay, so port impedance. Guys, we can see that the output resistance is almost 469, that means 470. It's a without bootstrapping output impedance. Okay. The bootstrapping circuit. This is a bootstrapping circuit where I connected from base to 100 kilo ohm. I am used this capacitor is a 47 microfarad. We can see that almost input is equals to output. Input is a 4.6 volts. And output is also 4.6 at a 10 kilohertz. Okay, and this there's no connecting any ohm. Let's connect a port, 1 meg port with series of 100 kilo ohm of 220 kilo ohm. It's above 500 kilo ohm. Okay, let's see that. Connected the port and this exactly reduces to half. Now we will calculate. Okay, so input resistance I series with 330 kilo ohm. Now let's see what is the input impedance. Okay, resistance of this total resistance. Oh, that's a guys, we can see that it's almost it's a 1.8 mega ohm. That's in a mega ohm. Okay, this is our input impedance with the bootstrapping. Without bootstrapping, we've seen that's around 700 800 kilo ohms. Now it's with bootstrap, it's in a we can see that it's a around 1.8 kilo ohm, right? So we will see output impedance with the bootstrap. Connected output port 1 kilo ohm port, and we can see that the output is exactly reduced to half of the. Okay, pick up the power supply and calculate the resistance, output resistance. You can see that. Okay, shoot. Yeah, that's in around 160 ohm. Okay, that's acceptable. That's a less than 470 ohm. It's a much more better output, less impedance. It's a good. Okay, guys, this is all about how the impedance varies, and we can see that we will we with bootstrapping around we are getting it's in a kilo ohms. It's in terms of 700 800 kilo ohms. With bootstrapping, it's in a 1.78 mega ohms. So it's a more improvement in a impedance, and we can see that in output impedance also much more lesser than our original impedance, that means 470 ohm. So this is all about the experiment Darlington Emiter follower. Thank you for watching. Please subscribe to Silicon Rays. Thank you.